Hi, this is Tom. Uh, Today I'm going to talk about a quantecon lecture. It's in the intermediate quantitative economics section. And um, I'm going to talk about a problem that stumped Milton Friedman. It's in this little suite of lectures called Statistics and Information. And it's going to build on earlier material about likelihood processes and frequentist and Bayesian statistics. So I'll I'll dive in here. Um, so this is a problem. It's a fascinating problem in the history of economics um, and in statistics. Um, Milton Friedman uh, was one of the greatest economists of the 20th century or ever, and he was also a very fine statistician. Um, he was on top of statistics when he was a graduate student. One of his uh, teachers at Columbia was Harold Hotelling. Uh, one of the He's an economist at Columbia, but who was also one of the founders of the foundations of statistics. Um, so Friedman was very well trained. He was a master of the state-of-the-art statistics. Neyman Pearson frequentist hypothesis testing had been invented in the late 30s. The tests of hypotheses, frequentist test of hypotheses using likelihood ratio tests. Friedman knew that like the back of his hand. Um, and during World War II, um, Milton Friedman, along with some other people, was working at the statistical research group at Columbia University, and some of the finest uh, statisticians at the time and some famous economists were working there. They were young men uh, at the peak of their scientific careers, and they were applying statistics to help the U.S. military um, make uh, basic operations analysis and improve their decisions about allocating resources. So, um, so this lecture is I'm going to give you a reader's guide to this lecture, and it starts with a Navy captain coming in to talk to and ask a question about some statistical procedures that he was asked to use. So there's a problem that this U.S. Navy captain presented to Milton Friedman and his colleague W. Allen Wallace, another great statistician. Um, and Milton Friedman and Alan Wallace worked on it for a while, uh, and they weren't able completely to solve it. And they handed it to a recent immigrant from Europe to the United States, Abraham Wald, a young man. Um, they gave it to Wald, and he was able to solve it. So in this lecture, we're gonna talk about that story. And in this lecture, we're gonna on Decode lecture. What it does is it talks about it from the perspective of a statistician working within the Neyman Pearson frequentist tradition. So this statistician thinks about testing hypotheses and using laws of large numbers to investigate limiting properties of particular statistics under a given hypothesis. And as we'll see, we've seen in other quantecon lectures, or if we've studied statistics, what a given hypothesis is a given vector of parameters that pins down a particular member of a manifold or class of statistical models. And so in another lecture, kind of a related follow-up lecture, we're gonna take the same problem, which is not what Friedman or Wald did. We're going to look at it from the perspective of a Bayesian statistician, who's not going to view parameters as fixed numbers that index an hypothesis, but instead he's going to view parameters as random variables. But that's not what's going to be going on in this lecture. Okay, so we're going to take a frequentist perspective, and the frequentist is concerned about relative frequencies conditioned on particular parameter values. And he's going to be interested in, he or she's going to be interested in exploring alternative hypotheses. So in this lecture, here's the ideas that are going to be in play. And they're the ideas that Friedman was right on top of. And that he was equipped with when the Navy captain came in. So what they are, type 1 and type 2 statistical errors. What type 1 is, it's the error that occurs when you reject a null hypothesis that is true. So when the hypothesis is true and you reject it, that's a type 1 error. A type 2 error occurs when you accept a null hypothesis that's false. So frequentist, Neyman Pearson, frequentist statistical theory is all about these two types of errors and what are the probabilities of these two types of errors in the frequentist sense. So we'll talk about the power, the size of a frequentist test, talk about the critical region of a statistical test. These are ideas in the background. The uniformly most powerful test. Those are the artillery that Friedman had. And the role of a law of large numbers is going to be at play. And the purpose of this lecture is to explain how Abraham Wald, using these ideas, proposed a quite different procedure than Neyman and Pearson had. So Neyman and Pearson have one set of procedures, the uniformly most powerful test. Wald is going to suggest something else, and he's going to suggest it because of Friedman's conversation with this Navy captain. So that's where we're going. Okay. So it's fascinating to read about the history of this problem. Okay, so Milton Friedman and his wife, Rose Friedman, they wrote a book, Two Lucky People. It's a joint autobiography, 1998. And they describe this problem. So I recommend looking at it. So there's larger than life figures. So there's also this article by Alan Wallace, who describes this group. And there's a new book about biography of Milton Friedman by Jennifer Burns. She describes this a little bit too. So let's listen to what Milton Friedman. This is Milton Friedman writing in the book. He says, in background of the story, look what he tells you. In order to understand this story, I'm just going to read this. It's necessary. This is Friedman, to have an idea of a simple statistical problem and of the standard procedure for dealing with it. And that was standard, actually, 1998 still, but it certainly was in 1942 or 3 when Friedman was young. The actual problem out of which sequential analysis grew will serve. The Navy has two alternative designs, say A and B, for a projectile. It wants to determine which is superior. To do so, it then takes a series of paired firings. It's called paired comparisons. On each round, it assigns the value 1 or 0 to A according to as its performance is superior to that of B, and conversely, 0 or 1 to B. The Navy asks the statistician how to conduct the test and how to analyze the results. So here's a standard answer, and it came right out of Neyman Pearson. It was to specify a number of firings, say 1,000, and a pair of percentages, 53 and 47, and tell the client that if A receives 1 in more than 53% of the firings, those 1,000 firings, it's a better one. If it receives a 1 in fewer than 47%, B can be regarded as a superior. If the percentage is between 47 and 53, neither can be so regarded. So the key thing is these numbers A and B and this decision rule. So when Alan Wallace, his colleague, was discussing such a problem with Navy Captain, here's his name, Schuyler, the captain objected that such a test, to quote Alan's account, may prove wasteful. But the captain says, if a wise and seasoned ordnance officer like Schuyler were on the premises, he would see after the first few thousand or even a few hundred rounds that the experiment need not be completed, either because the new method is obviously inferior or because it's obviously superior beyond what was hoped for after just a few rounds. So Friedman Wallace, they couldn't give him an answer. And then if you read this story, the background, they worked on it for about a week, full time. And it's fascinating. Milton Friedman said to Wallace, this is probably the most interesting problem we'll ever see in our entire scientific careers. But they didn't completely solve it. So realizing that, they told young man Abraham Wald, who was also working here, about the problem. Now, you should read about Abraham Wald, particularly these times when how a country thinks about treating and inviting immigrants into its country. Abraham Wald was a refugee from Europe in the late 30s and early 40s. He was in danger where he lived in Austria. He barely got out. He had a difficult time getting to the United States. He had some people helping him get to the United States and finding a job. It was very difficult for him. He barely got in. You could read about it. He turned out to be he was Kenneth Arrow's teacher. He's a brilliant statistician and mathematical economist. And the United States it became a scientific leader after World War II by welcoming refugees from other countries, immigrants from other countries. And anyway, there's a story there. You can see that's on my mind these days. So that's it. When Wald heard about this problem, he thought about it, and it led him to create this book, Sequential Analysis, which is a classic book. You see, it was basically written during World War II, but then written afterwards, and it's a classic. And we're going to walk in the footsteps to what we're going to do today is we're going to walk in the footsteps of Abraham Wald. So let's begin by reiterating the theory underlying the test that the Navy had told Captain Schuyler to use. We're going to use this as an occasion to listen to Abraham Wald describe mostly in words, Neyman Pearson theory. And so I'm going to quote from this book, Abraham Wald's book, Sequential Analysis. Okay, so when we listen to Wald, we're going to watch for these features of the setup. So he's describing Neyman Pearson's theory, Neyman Pearson theory, which the uniformly most powerful test. So there's going to be assumption of a fixed sample size. The sample size is fixed, and they're going to be applying laws of large numbers conditioned on alternative probability models. And that's what's going to be going on to interpret the probabilities alpha and beta of type 1 and type 2 errors to find the Neyman Pearson theory. So in earlier quantecon lectures or statistics class, we've seen these play a huge role. So Wald's he's gonna frame the Neyman Pearson problem as making a decision about or a choice of a probability distribution that you think is governing the data that is partially known. And again, you have to assume something is already known in order to state a well-posed problem. And usually something means a lot. You have to assume a lot. So by limiting what's unknown, Wald used the following simple structure to illustrate the main idea. So this is what he says. So we'll see. So a decision maker wants to decide which of two distributions. Wald calls them F0 and F1, govern an IID random variable Z. So Wald is going to assume IID random variables. But he doesn't know which distribution they come from, either F0 or F1. The null hypothesis is the statement that F0 governs the data. The alternative hypothesis is that F1 governs the data. So the null is F0 governs the data, the alternative. So the problem, Neyman and Pearson's problem, is to devise a test of H0 against the hypothesis H1, that's the alternative, on the basis of a sample of a fixed number, sample size of a fixed number of n IID draws of the random variable Z. Okay. So read what Wald said. Just to remind you, a test procedure leading to the acceptance or rejection of the null is simply a rule specifying for each possible value of the sample whether the null hypothesis should be rejected or accepted or rejected on the basis of the sample. This may also be expressed as follows. A test procedure is simply a division of the totality of all possible sample sizes, samples of size n into two mutually exclusive parts. Mutually exclusive, say part 1 and part 2, together with the application of the rule that the null hypothesis be accepted if the observed sample is contained in part 2. Part 1 is also called the critical region. Since part 2 is a sample, okay. So read this. Thus, choosing a test procedure is equivalent to determining a critical region. Okay. So then look what he says. So we're looking at a critical region. As a basis for choosing among critical regions, the following considerations have been advanced by Neyman and Pearson. In accepting or rejecting H0, we can commit two kinds of errors. We commit an error of the first kind if we reject H0 when it is true. We commit an error of the second kind if we accept H0 when H1 is true. After a particular critical region W, so he's going to call this critical region W, and that's going to be a set of samples. The probability of committing an error of the first kind, as well as the probability of committing an error of the second kind, is uniquely determined. Now, what does he mean by probability? E means relative frequency in a very long sample. The probability of committing an error of the first kind is equal to the probability determined by the assumption that the observed sample will be included in the critical region. And there we're going to apply, there the law of large numbers is applied. And you will see that later in the quantecon Python code. Okay. The probability of committing an error of the second kind is equal to the probability determined by the assumption that H1 is true, that the probability will fall outside the region. For any given critical region, we shall denote the probability of an error of the first kind by alpha, the probability of the second kind by beta. So he's reviewing to set up his problem. There's a lesson here. To set up his problem, he's going back and making sure that he's reminding himself and his readers of what Neyman and Pearson were up to. So what about here? What about the law of large numbers? What does it mean? What do alpha and beta mean? So here's Wald again. The probabilities of alpha and beta have the following important practical interpretation. Suppose we draw a large number of samples of size n. So when you ask where's the relative frequency, we're drawing a large number of samples of size n, repeated draws of the sample. Let m be the number of such samples drawn. Suppose that for each of these m samples, we reject H0 if the sample is included in W and accept H0 if the sample is outside W. In this way, we make statements of rejection or acceptance. Some of these statements will in general be wrong. If H0 is true and M is large, the probability is nearly 1, it's practically certain, that the proportion of wrong statements, i.e., the number of wrong statements divided by M, will be approximately alpha. If H1 is true, the probability is nearly 1, that the proportion of the relative frequency of wrong statements will be approximately beta. Thus, we can say that in the long run. So here's my comment. Here, Wald applies a law of large numbers by driving M into infinity. Our comment, and that's Wald. The proportion of wrong statements will be alpha if H0 is true, and beta if H1 is true. And in this statement, Wald is actually for us, he's writing pseudocode. He's writing Python or any Julia, any language. Pseudocode is telling us exactly how to write a program that will simulate what these statements mean. So the quantity alpha is called the size of the critical region for some reason, and the quantity 1 minus beta is called the power of the critical region. So alpha is always about some critical region or some test, and 1 minus beta is called the power. So here's what Wald notes. So look what we're doing. We're using Wald as our teacher or TA. One critical region is more desirable than another if it has smaller values of both alpha and beta. If it's got more power, I'm sorry. It has smaller values of alpha and beta. Although either alpha or beta can be made arbitrarily small by a proper choice of the critical region, it is impossible to make both alpha and beta arbitrarily small for a critical value of n, a fixed sample size. This is what Wald said. So this is going to, in an earlier quantecon lecture, we had our operating characteristic curve that showed this trade-off. That's going to occur again. So Wald summarizes Neyman and Pearson's setup as follows. Neyman and Pearson showed that a region consisting of all samples which satisfy the inequality, look at this. This is a likelihood ratio. A likelihood ratio strictly greater than k is a most powerful critical region for testing H0 against the alternative hypothesis. The term k on the right side is a constant chosen so that the region will have the required size alpha. Oh, this is a great summary. Um, so that's Neyman and Pearson's test, and what they show is that this is um, he goes on to discuss the concept of the uniformly most powerful test. Um, okay, so and this just gives you an example of how carefully and eloquently and elegantly Abraham Wald wrote. Okay, so now with this description as the background, so I'm gonna pause here to make some comments. Notice notice in this lecture the structure of how Wald proceeds scientifically. Um, he's going to do something. Um, uh, so first thing is he's going to end up criticizing Neyman and Pearson's procedure. But before criticizing it, he has to he's making sure that he completely understands it and is completely inside and outside of it, inside of it. So that's what he's done here. And now what he's going to go on is to do something new. But here's kind of the fact or irony. To do something new and creative, you have to begin by completely mastering what was done before, the best old things. And that's what Wald has done. So in Wald's sequential formulation, he's going to do something different. By way of contrast to Neyman and Pearson's formulation, in Wald's formulation, the sample size n is not a fixed number. Instead, it's a random variable. Now, if we kind of think back of what the Navy captain's suspicion was, this shows that Abraham Wald was listening really carefully, as was Friedman, to what the Navy captain said. So what he's going to do, he's going to have two parameters, A and B, that are going to be related to, but they're different from Neyman and Pearson's alpha and beta. So what A and B are going to be are they're going to be cutoff rules that Wald determines he's going to have A and B are going to be cutoff rules that are he's going to use to determine the random variable n as a function of random outcomes as they cut in. So he's not going to have a fixed sample size. And remember, Neyman and Pearson's test was all about a fixed sample size. So here's how Wald's going to set up the problem. A decision maker can observe a sequence of draws of a random variable z, and he can decide how long the sequence is. And go back and think about what the Navy captain said. The Navy captain said, I think what the Navy told me was not a good way to choose n. It had a fixed n. I think I can do better. And he's telling the Navy he could do better than their rule, and the Navy got their rule from the best statisticians at the university and the world, Neyman and Pearson. So the statistician wants to know which probability distributions F0 or F1 governs Z. That's how he sets it up. And this little lecture, we can have F0 or F1 be anything we want. We're going to have two beta distributions. So you can look those up on Wikipedia or somewhere. So a beta distribution has just this form. We're going to have two beta distributions. They have two parameters called A and B. And Python has tools for generating beta distribution. So here we're going to do some Python code. We're going to use JIT to accelerate things. And we're just going to plot them. So we're going to use these two distributions, F0 and F1. And later on, we'll change F0 and F0, but just by changing the values of the parameters. You see, F0, we had parameters A, B was 1, 1. F1, it's 9, 9. And You could see, you could, as usual, you can download you can come up here and you could launch this Jupyter notebook that does everything. You can come here, you could download the notebook if you have Python on your machine, but you can run this on Google Colab. You can follow these steps. Oh, so okay, so then here's the setting. Conditional on knowing that successive observations are drawn from distribution F0, the sequence of random variable is IID. But conditional on its F1, it's also idea. So, but so the what here's what the just like Neyman and Pearson assumed, uh, if on the hypothesis that F0 generated the data, the sequence is IID. On the hypothesis that F1 it generated the data is IID. But the decision maker doesn't know whether it was F0 or F1. So that means he actually doesn't know that the process is IID. He knows it's IID if he knew something else. Think about that. So we have another lecture called exchangeability and Bayesian updating. It's explained that the observer actually thinks that the sequence is not IID. He thinks it's called something called exchangeable. That's a little digression, but you might want to learn about that sometime. So consequently, the observer has something to learn, namely whether the observations are drawn from F0 or F1. So the decision maker wants to know which of the two distributions is generating the outcome, just like he did in Neyman Pearson. So again, so here's these type 1 and type 2 errors in this notation. And alpha is the probability of a type 1 error, beta is the probability of a type 2 error. I know that I'm repeating myself and this lecture repeats itself, but that's because I need to keep reminding myself and keeping straight. Okay, so here's going to be choices that we're going to get into. Okay, so I was going to frame it like this. Choices are after observing a sequence of Z's from Z1 to ZK, the decision maker is going to choose among three actions. And it's going to turn out that eventually K is going to be a random variable that's going to be chosen by Abraham Wald. So after observing K of them, he's going to decide that F equals F0, and he's going to draw no more Z's. Or he's going to decide that F is equal to F1, and he's going to draw no more Z's. Or he's going to postpone deciding, and he's going to instead draw an additional Z. That's what he's going to do. This is going to be a sequential test. He's going to keep drawing Z's until he either decides F equals F0 or F equals F1. So he's going to decide how big a sample he's going to draw sequentially. And that's Wald's idea. And notice how it's different than what Neyman and Pearson decided, recommended. So here's what Wald's going to do. He's going to define P0M. This is Wald's notation. I'm copying from Wald's notation. He's going to define the product of these marginal distributions, F0, 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 evaluated at Z1, ZM. He's going to define P1M, this, And he's going to try just to find the likelihood ratio of P1M over P0M. So that's a likelihood ratio, and this is LM is a likelihood ratio process. If we started at I guess 0 or 1, just keep on going. It's a likelihood ratio process. And then what Wald's going to do is he's going to have a sequential decision rule. It's going to parameterize by two real numbers, a B and an A. And then here's his decision rule going to be. His decision rule is going to be if the likelihood ratio is greater than A, he's going to accept F1. If the likelihood ratio is less than B, after M draws, if likelihood ratio is greater than A, he's going to accept F1. If the likelihood ratio is less than B, he's going to accept F0, and otherwise he's going to remain undecided and he's going to take another draw. So in this interior region, he's going to take another draw. So B is going to be a number less than A. It's going to set these two numbers. So a Wald likelihood ratio test is parameterized by two numbers, A and a B. And it's a region like this. On this axis, we're going to imagine this is the value of LM, the likelihood ratio at M. If the likelihood ratio stops here, he's going to keep going. If the likelihood ratio is here, he's going to stop drawing and he's going to accept F1. Here he's going to stop drawing and accept F0. That's his test. And his whole theory is going to be about, he's going to tell you what the consequences of picking A and B are. That's his test. Now, here's what might immediately come to mind. How is this A and B, Wald's A and B, related to Neyman Pearson's alpha and beta? If I kind of stopped here, that would enter your mind. So in chapter 3 of his book, Wald thinks about that carefully. And it turns out how A and B are related to alpha and beta, that's not an easy thing to figure out. But what Wald does is, with some math, I'm not going to go through it here, clever math, which you could follow if you read this, he's going to get an inequality. And the inequalities relate alpha and beta to A and B in this way. And notice this first inequality involves both alpha and beta, and the second inequality involves alpha and beta. So this relationship is nonlinear. So then what Wald does is he goes through a clever argument, and Wald was a great mathematician in every sense of the word. Kenneth Arrow, who was a great mathematical economist, takes his hat off to his teacher Wald. You can read about that. So Wald gets some approximations, and these are some rules. His approximation, he says, well, what I think you should do is you should set here's a recommendation that's going to have some properties. And these properties are going to, I'll tell you what the properties are, and we're going to investigate them a little later. Properties are A is going to be a function of alpha and beta. Will you tell me the alpha and beta that you want? And what you come in and say, well, I don't know about A and B, but I have alpha and beta. Mr. Wald, please give me some numbers. He's going to say, well, I recommend this. Take this, get me an A, take this and get me a B. And he says, for small values of alpha and beta, and notice, this is when you do approximation theory, you're often doing small values, and we want small values of both alpha and beta. Remember what he said is we want to make both alpha and beta small in the line above. He shows that this approximation provides a good way to set A and B. What does he mean by good? uh, what he says uh, this leads to conservative choices for A and B. And we're going to investigate that. He says it can't result in a big increase in the value of either A or alpha or beta. In other words, for all practical purposes, the test this and this, where those are those functions, uh, provides as least the same at least the same protection against wrong decisions of test corresponding to uh, to the actual the true relationship between A and B. Um, so what may happen is you actually may be running a larger sample size than you actually need to get the alpha and beta that you need. Okay, so that's going to be kind of the end of that's going to be the end of our description of what Wald did. Uh, so there's this test. So what we're going to do is we're going to fire up Python code, and we're gonna watch how. That's what I want. Uh, you could do that again, have more fun than watching me do this by either downloading the notebook or running this on Google Colab. So we're gonna watch how the Walls test performs under various conditions. So our goal is to understand trade-offs between decision speed and accuracy associated with this test. So so we're going to watch how the decision threshold A and B affects the average stopping time. And then, so we want to watch how A and B affect the average stopping time. And the um, and then we also want to understand how the discrepancy between these two distributions affects average stopping times. So we'll do special case where F0 and F1 are beta distributions, but you could rewrite the code that we have in quantecon and get whatever distribution you wanted. You could have two normal distributions and so on. Okay, so we're going to run a simulation, actually following Wald's recommendation or pseudocode. So we're going to compare log likelihood ratios to logarithms of the thresholds, which is since log's a monotone function, that's legitimate. So so here's our like kind of pseudocode. We're gonna compute thresholds A, this, and we're gonna work with log A and log B. And we're gonna, given a true distribution, we're gonna initialize a log likelihood function at 0. And then we're gonna over and over again we're gonna draw this observation from the true distribution. We're gonna update the log likelihood process using taking the old one and then adding to it the increment, the log likelihood ratio of the observation at time z. We're going to use this rule. If we're going to use his rule, if the log likelihood ratio is greater than log A, we're going to stop and we're going to eject. If the log likelihood ratio is less than B, we're going to stop and accept. And we're just going to keep going. Okay, and what we're going to do is we're going to repeat this for n replications. Actually, that n there was capital M. That was capital M in Wald's book. Well, actually, we could relate it to it, and we're gonna do it n. We're gonna have n of those n over 2 replications for each distribution, and we're going to compute the empirical type 1 and type 2 errors, alpha hat and beta hat, and then we're going to compare it. We're going to compare it with the alpha and betas that we wanted here. So these are going to be the target alphas and betas. Um, those are the target alpha betas. And remember, we're going to be using Wald's recommended formula. We have these target alpha and betas, and then we get these A's are associated with it. And then with that, look what we're doing. With that, we're going to actually figure out uh, uh, how good of estimate of these uh, are of the target alpha and betas. And remember, Wald told us that he told us that, well, these are going to be underestimates. These are going to be um, well, let's see. This is going to be uh, these are going to be biased estimates of the alpha and beta that are really going to prevail. Okay, so let's see. So here's code. Here's you can read this. Um, so again, we JIT it to make it fast. Um, you can read this, and nowadays you could, if you want, you could take this code and ask Claude or ChatGPT or DeepSeek to tell you what's in this code, and it'll do a very good job in English explaining this and teach you Python. Okay, so here's what we did. We did a particular example, and what we found is, boy, we stopped really quickly. We stopped very quickly for this. We could, if you look at this, we made up two particular distributions. Um, you could see what we did. Um, so look at this. Here's the Here's these thresholds we calculated. You could read this. Here's our formulas. We did the simulation. The average topping time was between either the first or the second. We stopped very quickly. The empirical type 1 error is only 0.01 when we were targeting 0.05. The type 2 error is 0.002 when we were targeting 0.1. So we find that um, the algorithm actually gives lower type 1 and type 2 error rates than the target values. Um, so just with this, we've gotten very close to the frontier because now there's work. Wald's sequential probability ratio test is very important. And there's he wrote that in 1947. There's a recent paper by some excellent researchers where they're seeing if they can get a better approximation, a better formula than this. So that's a research topic now, a state-of-the-art research topic. So they want to refine this approximation, and you could read that if you want to, but that's not going to be. So here's what we're going to do. We're going to get a graph that lets us visualize two distributions and the distribution of times to reach a decision. That's what we're going to have. So here's our two distributions. There's a beta, kind of some symmetry. There's a F0 is a beta 2.5. F1 is a beta 5.2. Those are the parameters A and B in the beta distribution. And here's this overlap region. So in this region, in this region down here, if you see an observation down here, you kind of it's very likely to have been from F0. An observation down here, up here, it's very likely to be of F1. But in this middle region, well, you can see which is more likely. But so here it's a tie. It's a tie, and in this region here, it's close. So here's the distribution of stopping times, and this is where the Navy captain said, "Well, you told me 1,000. I can make it much smaller." In this case, I could probably, if the distributions actually look like this, that's what he's telling him. I could tell you to stop after 5 observations. Okay, so with this same information that we've calculated, there's something that you'll see in machine learning in similar problems called the confusion matrix. And this diagonal elements count the number of times that Wald's decision will correct. It's the off diagonal elements uh, the diagonal elements are where it correctly counts, and the off diagonal when it makes a mistake. So what we accept F0 uh, when it's true over 98% of the time. We accept uh, F1 when it's true only 2.2% of the time, and so on. Um, so actually, and so on. So these row numbers are going to add up. These numbers are going to add up. So this is a confusion matrix. So we can use our code to study. What's fun to do is we could use the code to study different F0 pairs having different discrepancies between distributions. And so we can plot these graphs. All of these are graphs. So this is kind of a summary. So this kind of tells you everything that you want to know. Like, look at this. These distributions are quite different. And we stopped very quickly. Here's our confusion matrix and our error rates. These distributions are much more similar. And here we see this is a distribution of stopping times. The mean is higher, 11. So the closer we make these distributions, the longer is the distribution of, more drawn out is the distribution of stopping times. A random variable is the stopping time under the Wald test. And here's another one. Here's two distributions that are really close. See, we just did it by changing the betas. Now the distribution of topping times looks like this, and the mean is 42. So and again, here's our confusion matrix. And then here's kind of a summary about this. And then I'm just going to conclude by saying I'll let you look at the rest of this lecture. It's tempting to link this pattern to the Kullback-Leibler divergence applied to likelihood ratio processes, and we could think that well, here the Kullback-Leibler divergence between these two distributions is small, so so it's going to take a long time to distinguish the distributions. Here, the Kullback-Leibler divergence is very big, and it's going to take much less time to distinguish the distributions. And that's what's going to be talked about. That's going to be what's talked about at the conclusion of the lecture. So with that, that's kind of the end. So there's a lot to be thinking about here. And one way we might think about it is notice that this was entirely frequentist. And we could ask, my friend Tim Cogley would say, well, how would a Bayesian do it? And that's a good thing to talk about. We'll talk about that in another lecture.